Let's go ahead and restart. Thanks for joining us this afternoon. We have two talks again, same format as this morning. This morning, we had some nice discussion after the talks, and there were a few questions during, and that worked out fine. If it turns out there were a lot of questions during the talks, maybe I'll ask to wait till the end, but that format seemed to work pretty naturally. So we're led off this afternoon by Susha Parameswaran from Liverpool, and we already checked that your slides worked, I think. So please go ahead and take it away, Susha.
Okay, great. Hi, everybody. Thank you very much to the organizers for the invitation to contribute to this very interesting program. So I'm going to talk about string theory candidates for dark energy, and in particular, I'll be focusing on this proposal of thermal dark energy by Ed Hardy and myself. And I'll also mention briefly some other more or less promising string theory candidates. So my talk will be based on work done with my collaborators, Ed Hardy, Gian Massimo Tasinato, and Yvonne Savala, Jesenia Oguin, Bruno Bento, and Divya Chakraborty. Jesenia, Bruno, and Divya are our excellent students. Okay, so let me go straight into it. So the plan of the talk is to think about this question, given the difficulties in obtaining controlled de Sitter vacua in string theory, and we'll hear a lot more about that from Michael in the next talk, are there simple dark energy alternatives? So I will start by discussing briefly some of the challenges in realizing quintessence from a runaway string modulus, and then I will focus on the thermal dark energy proposal. So in developing alternatives dark energy models, we can hope to gain insights into the string theory landscape versus the swampland, and for example, the swampland conjectures such as the de Sitter swampland conjecture, the Transplanckian censorship conjecture that John mentioned earlier on. And of course, as we enter the era of new observations on dark energy and its equation of states, we can hope to have well-motivated alternative models in hand to test against the observations. Okay, so quintessence from a runaway string modulus. So whilst the past 20 years or more has shown us that metastable de Sitter vacua are hard to find, we know that runaway potentials are ubiquitous in string compactifications. So for example, string moduli are often supersymmetric flat directions, which are lifted ultimately, inevitably by non-perturbative corrections, giving rise to scalar potentials of this runaway form, where here I have shown the scalar potential for this parameter n in the Kähler potential is equal to 3 or n equals to 1. So when we see these runaway potentials, it's very natural to expect that we might be able to achieve some kind of simple Thoring quintessence scenario where the modulus field may find itself frozen somewhere along the tail of its scalar potential by the Hubble friction term in its Klein-Gordon equation, leading to an effective cosmological constant. Moreover, if that modulus field is in a hidden sector and sequestered somehow from a visible sector, for example, by some geometric separation in the extra dimensions, one can hope to avoid fifth forces and time variation of the fundamental constants. Of course, the devil would be in the details. However, it turns out that for these scalar potentials, these runaway scalar potentials from string moduli, the scalar potential turns out to be too steep to source quintessence. So when one works out the slow roll parameter for these potentials, the slow roll parameter turns out to be large along the tail. So what this means is that the modulus field can be frozen by Hubble friction along its tail, in the Klein-Gordon equations, but it turns out to be impossible for the field to be frozen and simultaneously dominate the energy density of the universe. So unless one were to fine-tune the initial conditions at the hilltop here, and note that this is at least a very simple example of an unstable de Sitter vacuum in string theory, okay, arising just from this supersymmetric flat direction lifted by a non-perturbative superpotential. Okay, so we've seen that non-perturbative runaway string moduli end up with a Kähler potential of this form, end up having a too steep scalar potential to source quintessence. There are similar results for other classes of string moduli, taking the leading contribution to the superpotential at the tail to be either non-perturbative, as we showed before, or perturbative. So these are some forms of Kähler potential which are very common in string theory, and it turns out that one cannot achieve slow roll quintessence at the tail of the corresponding scalar potentials unless one makes very special choices for the parameters appearing here in the Kähler potential and the superpotential. So it's worthwhile kind of making a comparison of, sorry, I'm not sure what you see. I see my subtitles here instead of the slide. Can you also, do you see the full slide?
I think we do, yeah.
Okay. So it's worth making a comparison to a non-supersymmetric scalar potential, so of just the leading runaway term of a non-supersymmetric scalar potential. Well, then one can achieve slow roll for a broader range of parameters. But what happens is that the four-dimensional supergravity turns out to constrain the coefficients in the scalar potential that descends from the F-term scalar potential in such a way that within supergravity, it's impossible to have a positive potential energy density and the potential to be slowly rolling. Okay, so I don't know how far I want to take that observation, but it's certainly fair to say that we do not yet have a working model of quintessence within string theory. I now want to move on to the main part of my talk, which is thermal dark energy. Okay, so I'm sorry to say that this will be the only time that I mention the elephant in the room, which is the cosmological constants problem. But okay, I'll hopefully still have something interesting to say. So, although the status of metastable de Sitter vacua in string theory and in nature is unknown, we do know that there are unstable de Sitter vacua in string theory. I just showed you a very simple example of an unstable de Sitter vacuum. And we also believe that unstable de Sitter vacua exist in nature. For example, in the top of the Mexican hat Higgs potential, and at the hilltops of the QCD axiom potential. Okay, moreover, we know that high temperature effects transform the unstable de Sitter vacuum in the Higgs's Mexican hat potential to a metastable de Sitter vacuum when electroweak symmetry is restored. So it's reasonable to expect that metastable de Sitter vacua generated by finite temperature effects are possible in nature, and thus in quantum gravity. In the case of our cosmological history, there was no accelerated expansion in the era when electroweak symmetry was restored and there was a metastable de Sitter vacua. There was no accelerated expansion because it turns out that the potential energy in the metastable de Sitter vacuum was dominated by the radiation energy density. But now we can ask, well, is it possible that there was some light hidden sector? There is some light hidden sector where thermal effects generate a metastable de Sitter vacuum, that now dominates the universe and drives an accelerated expansion. So that's what I'm going to discuss now, the conditions under which such a scenario is possible. Okay, so we know, of course, that string theory models can have hidden sectors which may have a rich internal dynamics, but be only very weakly coupled to the visible sector. So I am now going to suppose that the universe contains some light hidden degrees of freedom, which are still in internal thermal equilibrium today, so the interaction rates in the light hidden sector are greater than the Hubble expansion rates, and they have been so since reheating. This will constrain the hidden sector temperature with respect to the visible sector temperature, and of course, because they're only weakly coupled to each other, these temperatures can be different from each other. Okay, I'll moreover assume that my light hidden sector degrees of freedom includes a light scalar field, which may be a matter or a modulus, from a matter sector or a modulus field, and I'll assume that it has some potential energy function which generates some non-zero VEV for the field. So in particular, for the purpose of the talk, I will assume that my light scalar field has a Higgs-like potential with a Lagrangian mass parameter m phi and a quartic coupling. And then this scalar potential has a minimum when phi takes this value, this combination of parameters. I will call that combination of parameters phi 1. So the VEV of the field, phi 1. And I will assume for simplicity that I will take my constants in the scalar potential to be such that at the minimum of the scalar potential, the potential energy density is 0. So I'll tune it to Minkowski, and that can be relaxed to, for example, ADS vacuum. Okay, so I have a light scalar field. I'm also going to assume that the light hidden sector contains some number of light fermions and light scalars, other light scalars, which couple to phi via some Higgs-like interactions. So for example, some Yukawa-like interactions, some quartic interactions to scalars. And in particular, then the field phi generates effective masses for the fermions and the other scalars in the hidden sector. So the masses of the fermions and the scalars depend on the background value of field phi. So at finite temperature, when the plasma of light hidden fields will interact with the homogeneous scalar field background, and that homogeneous scalar field background itself determines the masses and the interactions of the particles in the bath, this then generates a thermal potential for our scalar field phi. So this is a picture for some conveniently chosen parameters of our 0 temperature scalar potential with the Minkowski minimum at phi is equal to phi 1 and a de Sitter maximum. Now for sufficiently high temperatures in the bath, in particular for temperatures larger than the masses of the fermions and the other scalar fields in the bath, then finite temperature effects contribute to the scalar potential of phi. So there are these finite temperature contributions to the scalar potential, which take this form. The coefficient B will depend on the couplings between the fields and phi. And for example, for the purposes of the talk, when I'm making plots and so on, I will just assume a single hidden Dirac fermion with Yukawa coupling 1. Okay, so for sufficiently high temperatures then, I generate this thermal potential, and moreover, this thermal potential can generate a local minimum at phi is equal to 0, provided that the temperatures are much higher than this mass parameter. So the minimum here at phi is equal to 0 is extremely shallow. Here I've zoomed in around phi is equal to 0 to show you the minimum. At very high temperatures, larger than the 0 temperature VEV of the field phi, phi is equal to 0 is a global minimum. So this is a picture of the scalar potential at very high temperatures, and you see the global minimum at phi is equal to 0. Okay, so then at finite temperature, we can shift the value for the field phi, the background value for the field phi, to its local minimum, and at that local minimum, we have a vacuum energy when phi is equal to 0. The potential energy, the background value for the potential energy takes this value, m phi to the 4 over 16 lambda. Okay, so now the hidden sector contributes to the Einstein's equations in two ways. We have dark radiation, which depends on the radiation energy density depends on the temperature, the hidden sector temperature, the hidden sector temperature today, and the degrees of freedom, the number of degrees of freedom in the hidden sector. And the constraints on dark radiation tell us that, in fact, the hidden sector temperature has to be less than the visible sector temperature today. Okay. As well as the dark radiation, we've seen that we have a dark potential energy due to the thermally shifted background value for phi, and we've seen that that potential energy takes this value. So then for thermal dark energy, we need that this potential energy matches with the dark energy scales observed. And this includes that it should be larger than the radiation energy density observed today. So we have this constraint on the parameters. If you put that constraint together with the constraint that the temperatures in the hidden sector are high enough to generate the local minimum and the metastable de Sitter vacuum, then we end up having a hierarchy of scales as follows. And in particular, I should point to the fact that the quartic coupling in the 0 temperature potential, the quartic coupling should be much less than 1. So just to give you some idea of the scales that we need for a hidden sector temperature of around 10 to the minus 5 electron volts, and a Lagrangian mass parameter of around 10 to the minus 6 electron volts, a quartic coupling around 10 to the minus 15, then we can match the dark energy scales today. And of course, we'll have an equation of state is equal to -1 today and in the past.
Sorry, just one quick question.
Yeah.
The requirement that your quartic coupling is very small, it's just because otherwise you don't develop a global minimum at 0?
It actually is rather coming from, it's a little bit more, I mean, there are a few steps to get there. So it's actually ultimately because of the observational constraints on the hidden sector temperature today.
Okay, I see.
So once you have the hidden sector temperature be less than this scale of 0.2 MeV, and then that also drives then a bound on m phi, and then to match the scales. It's actually more phenomenological to match the scale of dark energy.
Okay, thanks.
Okay, so those were the constraints in order to achieve a dark energy that matches today's dark energy. Then there are other phenomenological constraints. Okay, I also already mentioned and reiterated, thanks to Isabel's question, the constraints on dark radiation turn out to constrain the temperature of the hidden sector. And this is the constraint by the effective number of neutrinos depends on the hidden sector temperature, the visible temperature, the effective number of degrees of freedom in the hidden sector. For my very simple toy model, this is for a scalar field, and for the scalar field phi and my single Dirac fermion in the bath. And so it turns out that the constraints on the effective number of neutrinos from BBN for this simple model constrain the hidden sector temperature today to be less than around 0.3 of the visible sector today. Okay, so that's one constraint. Another constraint is that, of course, so we have only a very shallow local minimum here. And that then the metastable de Sitter minimum here will decay through nucleation of bubbles of the true vacuum. And we need that the rate of that bubble nucleation be sufficiently small, low, so that the lifetime of our universe is sufficiently long. So that bubble nucleation can occur either via thermal fluctuations up the hill or quantum tunneling through the barrier. And one can work out, numerically estimate the rates. And it turns out that for our working model of a Lagrangian mass around 10⁻⁶ electron volts, then the vacuum decay turns out to be negligible until the temperature, the hidden sector temperatures, for quite close to where the metastable minimum actually disappears. And that vacuum decay for our working model occurs at around n, the number of E-folds is equal to 4 in the future. So after n is equal to 4 E-folds in the future, then the thermal dark energy sector will decay, will go to the true vacuum, and the energy will be transferred to hidden radiation, hidden matter, and gravitational waves via first order phase transition. Okay, so here is a summary of what I said so far. Constraints on the allowed parameter space for our simple Higgs-like model from various directions. So notice first that actually the physical mass of our scalar field is not associated with the Lagrangian mass parameter, but with the hidden sector temperature. So this is constraints on the hidden sector temperature today, which is essentially constraints on the physical mass of our scalar field phi. And once we fix the dark energy scales, the vacuum energy to the observed dark energy scales, this then relates also our zero temperature Vev phi 1 to the Lagrangian mass parameter m phi, or equivalently the quartic coupling. Okay, so we've seen that the hidden sector temperature today is constrained by dark radiation, constraints on dark radiation, and there are further constraints from the existence of a metastable minimum. So the temperature, the hidden sector temperature, for example, should be high enough, of course, depending on the mass, the Lagrangian mass parameter, that the metastable de Sitter minimum be sufficiently long-lived, and that this parameter space is excluded by requiring that at temperatures, say, soon after reheating, the hidden sector temperatures are large enough so that the metastable de Sitter vacuum at phi is equal to 0 is actually a global minimum. So that would help to explain the initial conditions, how we ended up in this very, very shallow minimum compared to the deep minimum at phi is equal to phi 1. Okay, this is just a similar parameter space for another working toy model whose zero temperature scalar potential takes this form. And note that we can have really quite large physical mass scales for our field phi, around 10⁻⁵, 10⁻⁶ electron volts, compared to, say, quintessence scales of 10⁻33 electron volts. Okay, there may be further observational signals which I'll discuss a little bit. So one may have portal interactions between our thermal dark energy sector and the visible sector. So for example, there may be these renormalizable couplings between our dark energy field phi and the Higgs field, and there might be a series of a selection of non-renormalizable couplings. For example, this coupling between phi and the QCD gluons. So in particular, these couplings A and DG are particularly well constrained by fifth force experiments, and I give you here the excluded parameter space. It turns out that this coupling G is mainly constrained by the requirement that the hidden sector stays sufficiently cool to keep the dark radiation observations consistent. So this constrains then the coupling G. Okay, what I want to emphasize is that viable models are possible with interaction strengths, for example, this DG, which is not much smaller, not much weaker than Planckian. So, okay. And which, you know, we could hope to access these couplings, portal couplings, via future fifth force experiments. On the other hand, it's also true that these portal interactions would lead to visible sector loops, which lead to some UV sensitivity in the Lagrangian mass parameter m phi squared, and also phi tadpoles. And these contributions would destroy the dynamics that I've discussed up to now. So there's some tension between having couplings which are large enough to be accessible in future fifth force experiments and the need for fine tuning. So if the couplings are, if these portal couplings are large, then we need to fine tune the system. Okay. So I want to make a few more comments on the fine tuning before closing. I hope I'm not going to overrun too long, I promise. Okay, we've seen that dark radiation puts an upper bound on the hidden sector temperature. And this then leads to an upper bound on m phi and lambda. And however, the m phi, the Lagrangian mass parameter, and the quartic coupling in the scalar potential are UV sensitive quantities. In particular, the scalar field phi has to be strongly coupled to the fermions and the other scalars in the bath in order to generate these thermal potential, and those couplings would lead to hidden sector loops, which would drive the quartic coupling to order 1, whereas we've seen that we need lambda to be suppressed. However, it's possible to protect the system from these hidden sector loops by embedding the scenario in a supersymmetric model. So for example, if I assume that I have 2 chiral superfields with scalars phi and chi and fermions eta and psi, and the superpotential of this form with a supersymmetric mass parameter m psi and some soft SUSY breaking mass terms. And I'll assume that these soft SUSY breaking mass terms are much smaller than the supersymmetric mass parameter. Well, this system gives me a scalar potential of this form and some fermion mass terms of this form. And I'll assume that there's a suppressed hidden sector SUSY breaking scale, which means so the superpotential, this superpotential, and the mass hierarchy here will be protected by supersymmetry. Then, just as before, the finite temperature effects will favor phi to take background values that minimize the fermion masses in the thermal bath. And so for temperature, hidden sector temperatures much bigger than m phi, it will turn out that phi, the background value for phi, will shift to this value m psi in such a way to minimize the mass of the fermions. And once phi is 0, you will see that, phi is m psi rather, it goes from 0 to m psi. The potential energy shifted then becomes this potential energy, a non-vanishing positive potential energy, again, generated by the finite temperature effects. So that stability against hidden sector loops, one can also hope that there would be some stability against loops from visible sector states and heavy string states if there were sequestering of the supersymmetry breaking in the visible sector down to the hidden sector via, for example, some geometric separation in the extra dimensions. So, for example, if the gravitational mass were around 10 to the minus 8 GeV from low scale gauge mediation, then we would need this sequestering giving rise to around a suppression of 7 orders of magnitude in the soft masses in the hidden sector. And this is, of course, much easier to achieve than the levels of sequestering that would be needed in quintessence. Okay, so let me summarize and give some brief outlook. So the existence or not of metastable de Sitter vacua and or of quintessence in string theory remains a very interesting open question. Meanwhile, we've seen that a light hidden sector with finite temperature effects could explain dark energy with an effective cosmological constant with W is equal to -1 today and consistently with the swampland conjectures. So the hidden sector supersymmetry can help with fine tuning and much less sequestering would be needed than for quintessence. The thermal dark energy scenario needs a scale of around 10 to the -6 electron volts versus the quintessence scenario, which needs a scale of around 10 to the -33 electron volts. It's potentially observable via dark radiation and fifth forces. And the dark energy epoch will ultimately end, because our de Sitter vacua is only metastable, it will end when the hidden sector temperatures fall to around this Lagrangian mass parameter, and it will end with a first order phase transition towards the true vacuum. The conversion of the thermal energy will be to hidden sector radiation, matter, and gravitational waves. So this will happen at some point in the future. For the working model that we had, it's around n is equal to 4 e-folds in the future. So this then one then naturally begins to think, well, if there's a thermal dark energy era now, perhaps there were multiple thermal dark energy eras in the past with diverse hidden sectors associated with different energy scales. In fact, thermal inflation by Leith and Liddell would be one realization of that thermal dark energy era in the past. So this is one way that we might realize the early dark energy scenario, which turns out to be interesting to explain the H0 tension that's emerging in recent years between the direct measurements of the Hubble constant today and those inferred from the CMB. Earlier thermal dark energy scenarios are particularly interesting because they might have left gravitational wave signatures as each thermal dark energy sector transitioned to a global minimum via a first order phase transition, and one might ask also if there might have been other consequences of such a transition. And finally, of course, it would be important to embed the scenario more explicitly in string constructions and understand really how these finite temperature effects, the implications of finite temperature effects on the swampland program and the swampland conjectures. And I will end there. Thank you.
All right, thanks very much, Susha, for that very nice talk. I think we had a couple of questions that got put into the Slack channel, and anybody should feel free to jump in now. And if you did put a question in the Slack channel, please just go ahead and ask it.
Let me see if I can see the questions as well. Can I?
Michael, I think you just put a question in the chat. Do you want to?
I just put a question in the chat, and just as you had your elephant at the beginning. So first, I should say I really enjoyed this talk. But seriously, do you have some picture for embedding this story in a landscape, for example, or some other sort of cosmic history, even just broad, vague outline at this point?
Yeah, I honestly don't have a good answer for that. Honestly, I feel that whatever the solution to dark energy problem is going to also address the cosmological constant problem. And so this makes me feel that maybe thermal dark energy isn't going to be the solution. No, so I'm afraid I don't have a connected idea yet of how thermal dark energy is going to help.
That's a tall order. I'm not just curious of whether you have some general thinking.
Yeah, no.
Because I think the idea is quite interesting.
Maybe vaguely related to that, I'll ask, was the 4 e-folds, was that the thing that I was supposed to compare to the 140 from the talk this morning?
Yeah, I think it probably is, and I'm sorry that I don't have the number expressed in the right. So my guess is that it's going to be consistent, but it might be interesting to understand. It would be interesting to understand kind of the interplay with that and what the TCC conjecture exactly implies more generally. So my n is equal to 4 was just, for the simple toy model, and there's no reason why it had to be n equals to 4, no deeper reason. So I think it could be interesting to understand that interplay a bit more.
Do I understand right?
It's likely that the scenario would be consistent with the TCC conjecture, just because ultimately it's going to decay. So it would be interesting to understand.
And the ends tend to be fairly small in thermal inflation.
Yeah, that's true. So in thermal inflation, it's 10. The original thermal inflation had kind of 10 e-folds.
So can I do a follow-up question on that? Is that Patrick? Is that all right if I ask you?
Yes, please go ahead. Although we're hearing someone else's background right now, that I'm not sure who that is.
It might be me, actually.
Okay.
So of course, the people who wrote down the transplanting and censorship conjecture in Goya and Baffa also make the comment that it has something to say, some bearing on the cosmic coincidence conjecture. I mean, the very fact, we're living at the Hubble time when dark energy is first becoming dominant. It seems like from the numbers you have, it seems like you have a sharper version, an even sharper constraint. Is that true? Have you thought about the cosmic coincidence issue?
No, I actually did not have the feeling that I was going to help with that.
But the very fact you say it's going to decay in only 4 e-folds time means that we couldn't have been very, very much later. But then there's a question about, well, could you have lived with a much higher effective dark energy? See, the transplanting censorship stops you going much, much higher because it makes the rate of decay, you're forced to have the rate of decay much, much faster as you push the...
Yeah, no, that's true. So I don't know. I have not really explored the parameter space in that sense, like how many e-folds more I could push it. for different choices of masses and quartic couplings, for example. So I'm not, yeah, I have to think about it a bit more before,
Okay.
without,
Right.
you know, without.
Thank you. It might be interesting to ask it from this
Yeah.
perspective. You know, if you have new perspectives on old problems, I mean.
Yeah,
So.
yeah, no, that's, of course, that's, yeah, that's, yeah, it's a very interesting question. Yeah, I will think about it and let you know.
Yeah.
I think, Pratik, you had your hand up a minute ago and then that disappeared. I don't know if.
Yeah, I was maybe wanted to make a comment. First of all, thanks for a very wonderful talk, Susha. I really enjoyed it. But maybe this relates to Michael's question as well. The statement about whether quintessence in string theory is an open question or not. But I mean, the example I really like, which I keep repeating to people, is the fact that we know that there are so many extremely light axions that string theory compactifications point to. It seems that some amount of quintessence is almost inevitable in string theory, that surely there's like some extremely light axions which are displaced from their minimum to the end. We're rolling extremely slowly. And so I don't know, maybe whether this thermal dark energy idea plays well with trying to use some axiverse axions. But there's a very, very cheap and not fine-tuned at all option of having very light scalars which are rolling slowly today.
Yeah, thanks a lot for that comment. So I was kind of aware when I was preparing the talk, I haven't mentioned axioms, and that's, yeah, that's I needed to do it, but was there time? So in terms of thermal dark energy, we did try to think we did think a little bit about whether or not the scenario would be realizable with an axion, in the hope that that might also help with some of the fine-tuning issues. It turned out that it wasn't, that the way that the thermal potential, the thermal effects contribute, it doesn't end up shifting the axion values. In terms of axion quintessence, yeah, so it's of course an interesting proposal. So I have, you know, yeah, I don't know how far one can take it in terms of, you know, the constraints and the weak gravity, the axion versions of the weak gravity conjecture. So if you'll need large axion decay constants to achieve the slow roll, and then usually that might require some kind of alignment mechanism or other mechanism, which then takes you back to the problems that we had with a de Sitter vacuum, where you need to kind of delicately balance different effects against each other. And the alternative is an alternative is the hilltop scenario, which, and again, you have to address the initial conditions. So yeah, it's certainly interesting, but I haven't found it as compelling as I would want.
But especially for the late universe, you don't need that large an FA, and that
that's true.
A very like 10%, 50% tuning of the initial misalignment gives you a consistent late time cosmology. Inflation, like you point out, has all these other large field and then hilltop and all sorts of fine tunings built in, which maybe makes it less compelling.
Yeah.
Thank you.
No, thanks, Steve.
All right, we have time for maybe one more question if there is anybody or a comment. Okay, then if not, let's thank Susha again. Thank you very much, Susha.
Thanks, everyone.